Here's a pretty basic population growth problem. We'll be talking about people population growth, but this also works for bacteria, anything that's growing exponentially. And you just change the time from hours to years or whatever it is. It's all in elapsed time, so it doesn't really matter which version you choose. In this case, we're looking at millions of people, could be thousands of people. You can just leave that millions or thousands off and deal with the number in front of it, which is the easiest way to go and how we'll be doing this particular problem. So in 2020, the population of a certain country is 23 million people, and the exponential growth rate is 2.19% per year. We want to find the function that models that. You can either do this as a straight up growth rate 2.19% becoming your base, but we're going to use E because E is in our calculator. We don't have a 2.19% exponential function on our calculator, so we're going to change it into base E. The basic population formula, actually the basic exponential equation function, looks like this. A of t equals a naught e to the kt. A naught is the initial amount. That little zero there stands for when t equals 0. So you're looking at the amount when t equals 0 for that number. And then e to the kt, k is the exponential growth rate. And it's actually just a change of base factor from going from your actual growth rate to base E. T is the amount of time since A sub naught occurred. So whatever that elapsed time is. So here is our function. We had to change the percent into a decimal number, as we normally do. Stick the starting value in for A sub naught, and that's our function. Part B of this problem is, in 2025, what does the model predict the population will be? So 5 years have passed since 2020, so that's the elapsed time. So we're going to be putting 5 in for t, put that in your calculator, and you get 25.66. And you need to remember that you're talking about millions of people here. Again, that's contextual with your problem. So to find out how long it's going to take for the population to double, this time we're going to be solving for t. So we started out with 23 million people. So if we double that, we'll have 46 million people. So the ending amount in this case is 46, and the initial amount is 23. That gives us a doubling. And the rest of the equation is the same. If you divide both sides of the equation by 23, you end up with 2 equals this. And you'll see in some textbooks where they want you to just start with the 2 there. That works, but sometimes you're asked to not do doubling, but to find out when it's 65%. So I like to do it out because it works in any specific case, not just for doubling. So now we have a number equals e to an exponent. We need to get that t out of the exponent. To do that, to get a variable out from inside of a function, we apply the inverse function. So we apply natural log to both sides of this equation. And we get natural log 2, and then the equals, and the natural log and the e, those are inverse functions, so they undo each other, and we're just left with the exponent. Divide both sides by 0.0219 and put that in your calculator. You get 31.65 years. I'm going to round that up to 32 years and add it to 2020, and that gives us the year when the population will be double.